Good morning, everybody. I'm David Hosansky. I handle media relations for the National Center for Atmospheric Research. Thank you, everybody, for coming out this morning. And for those following online, thanks for joining us. So this morning, we've got a panel of leading scientists from NCAR, National Science Foundation, NASA, and we'll have a kind of traditional press conference format. Each of them will give some brief opening remarks, and then we'll open it up to Q&A, both to the reporters in the room as well as to the folks online. When the press conference is over, we've got a room full here of scientists from across the country who are going to be studying the eclipse. They'll be available for follow-up questions. If there are folks who are following this remotely, have any follow-up questions, you're welcome to reach out to me and we'll get those taken care of. So this morning, the speakers, we've got Dr. Scott McIntosh, who is director of the High Altitude Observatory here at the National Center for Atmospheric Research. He'll be followed by Dr. Carrie Black. She is the associate program director for NSF's Division of Atmospheric and Geospace Science. And following that will be Dr. Lika Guhata-Gurta, who is the lead scientist for the NASA lead scientist for the 2017 eclipse. So with that, I'm going to turn it over to Dr. McIntosh.
Thank you, David. Good morning, everyone. It's my real pleasure to stand in front of you and give a little overview of today's events and also of the eclipse itself. Little brief format. Note that, of course, the first section of this is a more traditional Q&A press conference featuring myself, Carrie, and Lika. Following that, we'll wish you to join us in the atrium to mingle and talk about the various science experiments that are taking place. And then finally, possibly the most challenging thing to my peers in the audience is the Ignite session that will follow and will be webcast. And that is a fairly challenging enterprise for everyone, as it's 20 slides, 15 seconds each in auto advance. It's a true challenge, and I'm not sure how many of my peers have tackled this one before, but it should be exciting and fun to follow. Now, of course, if you live under a rock, or you live on a rock, wait a minute, you may be wondering what a total solar eclipse is. It is a ballet of celestial order involving the moon, the sun, and the earth. The orbits of the three often combine, not every month, but once approximately every 18 months, the shadow of the moon blocks out the light from the sun because of the angular dimension of the two. Just by quirk, the diameter of the moon is about 400 times less than the diameter of the sun, and the moon is about 400 times closer to us than the sun. So by accident, when the orbital variables agree, you get an eclipse, and that eclipse casts a shadow on our planet. And we're going to see one on August 21st, so exactly 1 month from now. This eclipse has been dubbed by many the Great American Eclipse. It's the first to cross our country in a long time. It will span 14 different states, and it starts on the west coast at about 10:16 Pacific Daylight Time, transits the country, and leaving the east coast at 2:47 Eastern Daylight Time. It takes 91 minutes to cross the country. There's a 2.5 minute average totality. The path of totality, the actual deepest shadow of the moon, is only about 65 meters across, and the place of greatest eclipse is in Hopkinsville, Kentucky. The neat thing about this, as a scientist and someone with kids, is that the whole lower 48 will be in shadow. So that means everywhere in the country will experience at least a partial eclipse. And so it's an unprecedented time for myself and my peers to talk to the public about eclipse science and the sun and its connection to our planet. Eclipses help us to study the sun's corona, and of course I'm cheating here because this movie that's playing is with an artificial eclipse. It's an instrumental eclipse called a device called a chronograph that was devised back in the early 1940s to study the connection of the Earth and its impact on our upper atmospheric ionosphere and the ability to send radio waves across the country. You'll hear some talks about that later and posters out in the atrium. You may or may not know that we actually live in the sun's corona. That is a fairly blustery environment, as you may have guessed from the last slide. And that sun, that object, the thing at the center of the solar system that's constantly evolving, places our technologically dependent society in peril almost daily. Our power systems are vulnerable to solar events. Satellite communications and other satellite payloads and astronauts in space are vulnerable, but possibly also things like the money markets. And so it's vitally important to understand that ongoing connection between the sun and the Earth and its tempestuous variants that we have called space weather over the last few years. Here at HAO, which just happens to be the world's oldest solar terrestrial physics organization, we are studying the corona. In fact, we've devised a plan for a new observatory called COSMO, which will use these artificial solar eclipses to study the magnetism of our star, how it becomes unstable, how it erupts, and how those events propagate into space and then impact the Earth. I cheated. The little movie playing in the bottom is a little bit of a cheat when you use these artificial eclipses. Everybody wants to guess what the solar eclipse is going to look like. But often, like many things, the best way to figure out what the eclipse is going to look like is to look at what the sun looked like from Earth 27 days ago. And so the little montage that's playing down in the bottom corner are the last 7 solar days. Next week, we'll be able to look at the last solar day before the eclipse and probably make some kind of prognostication about what the shape of the corona may look like that may help our colleagues when it comes to pointing for the event on the 21st of August. I have to give a little bit of a shout out to one of the teams that isn't actually here today in person. The AirSpec team from the Harvard-Smithsonian Observatory is a partnership between HAO, SAO, the NSF, and our colleagues in the Earth Observing Lab of NCAR. You will see in the top right-hand corner that they're flying the NCAR Hyper G5. That is the NSF's aircraft that operates field campaigns with NCAR. It is the first of its kind. It's an experiment to study an eclipse, full-on scientific experiment to study the infrared corona, far infrared corona, from an airplane chasing the eclipse at about 50,000 feet in quite quickly. Unfortunately, it's not supersonic. But the project has been led by Ed DeLuca at SAO, and in large part is down to the dedication and effort of Jenna Samra, a PhD student, who is currently down in Broomfield integrating her instrument with the plane, and you can understand that timelines are so tight that she wasn't able to join us this morning. The experiment working perfectly, and I believe should it be successful on August 21st, it opens the door to a brand new platform for eclipse science and brings our organization closer together as solar and heliospheric physicists join with terrestrial physicists and chemists to do more eclipse studies. And so, as you may or may not have guessed, because I've talked about artificial eclipses and I've talked about natural eclipses, these natural eclipses offer an opportunity to push technological envelopes, engage the public, and get a stronger sense of the unending connection between our sun and us. We have a chance on August 21st to take very, very new technology and put it in the field and test it without having to build a complicated, very expensive artificial eclipse mechanism. So it's really pretty cool to see all the experiments that are going on and you'll hear about later. And so I think, for me, that's it. and I will hand over to my colleague, Carrie. David, I'll cue you up.
Thank you.
Do you want to end with that one?
And end with thank you.
Yeah.
Excellent. Thank you, Scott. Thank you all for being here. Thank you to David for all of his hard work on this. I'm from the National Science Foundation. Very fortunate to work in the geospace section, and we are largely responsible for funding science that covers everything from the surface of the sun to the Earth. It's pretty amazing. Since the sun is also a star, the Astronomical Sciences Division at NSF also supports the studies of the sun. So it's pretty exciting. There's a lot of support for solar physics at the National Science Foundation, and we have the great fortune to partner with NASA Heliophysics Science Division as well. We work very closely with those folks. Great American Eclipse on August 21st is such an exciting event. It is a really singular and unique event in human history, really. We're in the 21st century. We have this amazing technology. We have social media, and it's happening across the United States. So the entire country can participate. There's never been an event like this in human history where so many people could participate and with such unique technology. There's a lot of citizen science projects that are happening. Folks can participate through the Citizen Kate project and through Eclipse Megamovie, which is a partnership between Google and University of California at Berkeley. The NSF has partnered with American Astronomical Society to provide a series of mini grants for folks to do eclipse science on their own. And the AAS has fantastic resources for people to get involved. I would recommend checking out their websites if you haven't done so already. We're expecting millions of people to participate in this event, and images and data from this will be collected and analyzed by scientists for years to come. So we're very excited about everything that's going to come out of this. What's particularly special about a natural eclipse is that the moon is a perfect occulter. So it blocks the surface of the sun just perfectly so that you can see very low into the solar atmosphere. And this is really different from man-made occulters. So these man-made occulters are called coronagraphs. But usually they're made a little bit larger than the surface of the sun because you want to protect your instruments. And it's very difficult to align them exactly perfectly. So these man-made occulters tend to block out the very low corona. And scientists are particularly interested in the low corona because that's where lots of activity is. And that's where the origins of space weather are. So space weather is very important in the in the national eye right now. It's a very big deal. The federal government is investing a lot of money and organizing folks to try to protect our communication satellites, our power grids, these types of things from space weather events. There's a lot of eclipse science that's happening. Of course, that's what I'm interested in at the National Science Foundation. This particular eclipse is being used for instrumentation testing and for crowdsourcing experiments. We don't usually have opportunities to take advantage of so many people being involved in a singular event. This is being treated as a natural laboratory. Some of the really unique studies that are happening are studies of the ionosphere. So this is a charged layer of Earth's atmosphere. And the ionosphere is created because there's driving from the sun. So the sun impacts the atmosphere and charges particles. But when the eclipses happen, there's no more driving from the sun in a particular region. So the ionosphere in this region disappears, they say. It forms a cold spot. And the shadow creates this cold spot, and ripples are expected to form from this. And so folks are going to study that, particularly Josh Semeter at Boston University. He's doing a proof of concept using massively crowdsourced space weather observations. So they're going to try to leverage GPS signals from smartphones to do this, which it's really interesting. I can't wait to see what comes out of it. There's Eclipse Mob, which is being run by Kirsten Kirby Patel, who I believe is here today. She's involving high school and college students in ionospheric studies. They're going to make measurements during the eclipse as well. And then, of course, there's NCAR's Gulfstream 5 and the AirSpec, which is happening. And that's looking for candidates for heating and accelerating the solar wind. This is an outstanding problem in solar physics right now. So we're very excited to see what comes of that. Finally, the Astronomical Sciences Division is building the world's largest solar telescope, the Daniel K. Inouye Solar Telescope. This is being built in Hawaii. It's going to act like a microscope on the sun, so it's going to have a small field of view, but take very high resolution images. So we're really looking forward to the fundamental science that we can get out of this. It'll be unlike anything we've been able to measure in the past. First light is expected in early 2020, so fingers crossed for that. Look forward to it. So looking forward into the future, crowdsourcing techniques are going to be tested in this eclipse that we're hoping we can use in the next solar eclipse that happens in 2024. That one's only along the East Coast, but we're hoping lessons learned from this will help make even more exciting measurements in the future. And at NSF, we're continuing to support investigations of the sun and space weather. We cannot wait to see what sort of exciting science comes out of the measurements that are made in a month. And that's it. Thank you very much.
Thank you very much for being here and for the invitation extended to me. I first would like to give a shout out to my old alma mater, High Altitude Observatory, where I was a graduate student many solar cycles ago. And this is the place that actually pioneered the coronagraph. In fact, I started out being a graduate student of Gordon Newkirk, who flew many coronographic instrument. So coronagraph, in a way, is in my blood, and the science of coronagraph. And what I'd like to do here is give you a perspective of all the things we are doing during the eclipse, just not studying the sun, just not the ionosphere, the land around us, the birds, the animals, the social behavior. Just as it takes, a village to raise a child, as has been said, I would say that it takes the entire continent of USA to really gather the information of various kinds, scientific, but science, soft science, psychology, animal behavior, to really fully understand how intimately we are connected to our star. And so I'll just give some basics. And why is NASA interested in this? I think this was sort of what is going on during this eclipse. It's not a NASA event, but if you think about it, its reach, it is as if NASA was directed to do this. It's in the 1958 act of when NASA was created. I think our basic goal right now is safety, because pretty much everyone in the continental USA, Hawaii, Alaska will be able to see this eclipse, mostly though partial, and that's where safety is absolutely vital. Of course, science is our big thing, awareness of mission, science, and return on investment. We are supported by taxpayers. Education, fundamental learning opportunity of nature's processes. In a way, we are not able to connect these disciplines. We kind of practice stovepipe discipline, but this eclipse provides us an opportunity of interdisciplinary science. Public engagement, I cannot think of any other event that will have a greater reach, and I really do compare it to the moon landing back in '69. and citizen science. Today, we are able to, with our technology, to allow the participation of students and everyone else and engage and contribute to the science that we do. And some of these are actually basic science. Very quickly, this is just a picture of sun. You have already seen this. Let's see if I can play this movie. Will it play? Yeah. All this is doing, giving a picture of sun in time. I don't think it's moving, but what you saw is the pale yellow ball of the sun that we are used to seeing, and that's why most of us think sun is a really dull, boring star, other than the dark spots, the sunspots that we see, which we can sometimes see with our naked eye if the spot is large enough. But we also see the sun in different wavelengths, like ultraviolet or soft X-ray, and that's where you begin to see the dynamic nature of the sun. And that's where the magnetic field of the sun plays a very dominant role. And what happens is when the magnetic field varies over a cycle of 11 years, it creates radiation, photons, magnetic field. This is an interesting situation. And so what you're looking at here is our outermost environment, the magnetosphere, really being compressed by the particle pressure and radiation from the sun. So it's quivering like a cocoon. We are sheltered by this magnetosphere. If we didn't have this magnetosphere, some of this harmful radiation would percolate through, and it does happen every once in a while when the magnetic field lines between the sun and earth are just perfectly aligned. And that's the reason we see northern and southern lights. But it's not just our planet that lives with this tempestuous star. It is the entire solar system. Now we are learning what happened on Mars, or what was the weather on Pluto when the spacecraft arrived on Pluto. And as we study the sun and its variability and create models that can go into the outer edges of the solar system, we are able to kind of forecast at least rudimentary aspects of the behavior of the heliosphere. I had to put this in simply because I brought up HAO. This is a picture in my thesis. This was in Time magazine in 1988. Eclipses also have cycles. Every 18 years or so, you heard Saros cycle. This is eclipse 139, and this was part of my thesis. But the picture that you're looking at is more than that. It's a white light coronagraph image taken from HAO, and inside what you see is the first soft X-ray image of the corona. And this is a superposition of those two. This had never been done before. Today, we see dime a dozen, pictures like this, because NASA is eclipsing the sun in different wavelength, 24/7 essentially. But this was the first picture. I have 5 minutes. I'll go very quickly. This is a visualization giving you the path of totality, and the crescents there are essentially giving you an idea what kind of partial eclipse you are going to observe if you're away from the path of totality. The pink band is the path of totality. This is an interesting slide. I'm not going to talk to it, but you can see, if you can read that, pretty much everyone has access to this eclipse, partial or total. Traffic is going to be a nightmare. Eye safety, have to put this out. Not going to talk about it. There is only one time during the eclipse that you can take your glasses off, and that is during the phase of totality. If you're planning to drive anywhere, take a look at what the cloud conditions are going to be coast to coast. This is actually from the Department of Transportation. I would urge you to actually go to these websites if you're planning to drive to the path of totality. This is a chart that actually shows all of the NASA real-time activity and broadcasting that will be going on across the path of totality. And the blue ones are subject matter experts, the green ones are actually live broadcasting that will be happening. So why NASA? Few ideas: seeing the sun, observing from the ground, observing Earth. We are going to study the Earth, study the moon, planetary eclipses. And of course, by extension, by studying the sun-earth connection, we can take it to sun-planet connection, as we are already doing, but also exoplanet. It is the connection between that exostar and its exoplanet, and what's the dynamic nature of that. This is a movie that was created to kind of give you a view, essentially, of many of the things that NASA is contributing to, along with all our partners. We have many operating spacecrafts that will be observing the sun for sure, but we are also be observing the shadow on the Earth from our Earth science missions. We will be observing the ionosphere. We have about 60 balloons strewn through the 2,500 miles across that students will be launching. We have airplanes that will take first ever infrared observations from an airplane, I would say in this wavelength band. Look at Mercury, something we can't study under any other conditions. Not going to go through this, you kind of already know this. These are the basic features on the sun that we study when we look at the total solar eclipse. And the question is, why is this so important? It's because we cannot really see the very edge of the photosphere where solar wind and solar corona begin to expand, accelerate, and corona is heated. That's what sets the boundary conditions of how this is going to expand into heliosphere. And this is the source region of space weather. It is extremely important that we get those measurements. Let's see. These were kind of 11 of our proposals. Many of you are here who will be giving Ignite presentations. These are, again, through the eyes of NASA. We have solar observations. We'll be observing the eclipse from the ground, globe measurements, really taking temperature, density, wind velocity measurement. We will be testing new instruments, new coronagraphs. We have projects like iNatural, partnering with California Academy of Science to really detect animal behavior and record them. This is a fascinating plot that kind of gives you the insolation. It's actually fall off of the solar brightness as the shadow approaches. When this happens, of course, everything on Earth is going to be affected. And it's not just a day-night cycle. This is happening over a period of about 4 hours, but it also affects animal behavior. And on one example, I'm not going to talk to it. This is just to whet your appetite, the cool stuff we are doing, already preparing for this eclipse. Carrie already talked about the ionosphere. Well, what exactly happens during ionosphere? It's like a cloud coming in front of the moon acts as a cloud. When we have cloud, it blocks off radiation. And moon is acting similarly. And this is a control experiment, essentially, but I can talk about it later. This is a very, very cool movie that I have to show briefly. And what this shows you are what we are learning through our missions like LRO on the moon, which is giving us a detailed map of the umbral shadow. Normally, the umbral shadow has been sort of round. But now that we know the details of valley and the mountains on the moon, and as it interacts with the topography of Earth, you are seeing actually it's a polygonal shape object. It's no longer. So where you're going to be matters. It's not a circle. It's fascinating. You should take a look at it. Not going to go over this. You can take a look at this. Outreach activities, many of these are listed here that you should take a look at. But I do have a couple of more slides that I do want to go through very quickly. And this is, how coincidental is this? We just don't depend on nature only. I mean, human ingenuity. We will be launching Parker Solar Pro Plus to the sun. It will actually get to the corona where the very region that we will be seeing with our naked eyes during the total solar eclipse. And you're seeing that parabolic path right there within 10 solar radii. It is pretty incredible to really understand and attempt to kind of give description to the question, why is the corona so hot? what accelerates the solar wind. Another thing that has happened, this is the citizen science aspect of it, first ever thermochromic ink stamp. Can you believe we have a stamp that has been issued? If we wanted to get the word of eclipse out to the entire continent of USA, then with one swoop, I think the US Postal Service has actually done that, brought it to our hand. And finally, I would like to say that as a singular event of national scale and with a global audience, this event will rival the moon landing of 1969 as a landmark event for a new generation. At least that's my hope. Thank you.
Thank you, Lika, and thank you, Scott and Carrie. We're now at the Q&A portion of the press conference. Are there questions from reporters? And for those in the room, please use the mic.
Hi there. Hello? Can you guys hear me? Okay. Hi there. I'm Nick St. Fleur from the New York Times. Thank you guys for putting this together. One of my main questions focuses around citizen science. So I've been kind of doing a bit of reporting on the eclipse for several months now, and I'm pretty excited that I'm getting to the point where and Uber drivers know this is happening. But people are very excited to see how they can kind of contribute. Which of the several citizen science projects happening would you recommend someone who just learns about the eclipse a week before, 2 days before? Which of these projects do you think takes the least amount of, I guess, effort to learn how to do and to participate in? And then my follow-up question is, there's going to be hundreds, maybe even thousands of people contributing to this science. How will NASA and NSF and all the solar physicists make that data that's collected publicly accessible to everyone who's helping collect it? Thank you.
Good question. I'm particularly biased because I'm involved in a project called the Eclipse Mega Movie Project. And the Eclipse Mega Movie Project spans all the way from professional photographers down to, is my phone under there? Smartphones. And so there's an app that's been developed. And so in principle, you can pick up that app and become a participant. And it's probably more like millions, maybe tens of millions of participants. The plan following the eclipse is to gather the data, the images, sequence them in rather short order. In fact, I think the goal is to have a proto movie out that night. We're seeking also to have appropriate accreditation. So there'll be a little scroll bar with thousands of names. You know, you get the idea. And then the data will be served on a server, hopefully here, for posterity and for everyone to access. So that's at least how the mega movie is proceeding.
In fact, I have some answers to your question in my slides that I just flipped through very quickly. I think the easiest thing would be to use an app. So there are lots of apps available. If you go to the NASA website, eclipse2017.nasa.gov, they are kind of partitioned, both on Android device and iPhone. The Globe project has really cool apps that kind of makes the connection, right? You're seeing a drop in temperature as you're standing in the shadow, and it goes down quite a bit. You will, if you are actually in the deep umbra, you are actually going to sense difference in microclimate as a consequence. There's the iNaturalist app from the Cal Academy that you can take to go to a zoo. It's a summer day and record the animal behavior. What are they doing? I mean, from little creatures to big creatures, you know, they respond to the changes in ambient light. There's a Google journal where a lot of this experience and information are being dumped. We have lots of plans, but you know, the final thing will happen once we have collected all of this and figure out who or how best to serve this and collate this. But please get the word out.
Definitely, everybody should just take as many pictures and as many movies as you possibly can. Even if you can't get them up immediately to things like Eclipse Mega Movie, there will be lots of opportunity for folks to make their data available. Post it on Facebook, on whatever. There should be hashtags. I don't know. Does NASA have a hashtag for it? Yeah.
We'll create one.
Okay, good, good.
But I think also there's this aspect of the sound. We have, I believe there's a project called Soundscapes, or where it's for for blind people, so that they can also interact. And for those of us that have seen an eclipse, looking around the room for a brief indication of how many, but the sound, the change from the nervous anticipation to silence to 4th of July, hooping and hollering, to almost depression at the end when it goes away again. But to capture that, and I believe a lot of the apps also capture the audio as they're taking the visuals, and so it should be pretty awesome to be able to put all that together also for context to the people who can't see it.
I'm sorry. We just have a question, I think, from one of our web followers.
Yeah, we have a couple of questions from Ryan Mandelbaum at Gizmodo. Ryan, I'm unmuting your line.
Hey guys, it's Ryan. God, I heard all you laugh as soon as they said my name. But my first question is just, I wanted to basically what folks learned from eclipses. I know that we're very excited about the coronagraph now, and I know the general relativity had measurements that were made back in 1919. But I'm interested in what other sort of advances have been made, in past eclipses. What other sort of advances have been made, in past eclipses?
So I don't know that I heard your question completely. I don't know whether you want to go back in history or you're talking of the present. But historically, of course, there have been some remarkable discoveries that you might already know. How the corona is hot came from eclipse. We verified general theory of relativity. We found helium, so it goes on and on. In the recent present time, actually, we are developing sophisticated instruments. We can't fly new technology, new instruments in space just like that because it's very expensive. Eclipses offer us that opportunity to test new equipment. Like we're testing coronagraphs with filters that will actually measure the so-called polarized brightness, for which typically we have filter wheels, removing some of that. That's pretty interesting. We're going to measure temperature, velocity, density together. These are important ingredients for science. We are going to measure the solar corona in infrared, both from ground and from space. And that is going to allow us access to what the magnetic field might be in the corona. Remember, the corona is shaped the way it is because of magnetic field, and we really don't have any good idea other than our remote sensing observations and models as to what the magnetic field might be. The infrared observations is definitely going to add to that. We have deposition of waves, magnetic and sound waves, that we believe could be adding to what hits the corona. One of the experiments on WB57 actually is directly going after that by taking measurements like 30 times per second, really to measure, are we seeing waves? Are they coming towards us, moving away from us? So there are lots and lots. I'm going to stop with that.
Yeah, hi Ryan. There's one little added bonus to this eclipse, that just to the southwest of the corona, or just in the corona to the southwest limb about 4 or 5 o'clock, there will be a star. In fact, that will be the brightest star in the sky, called Arcturus. And it will act as a beautiful calibration source for those brave enough to go and redo Edity's experiment. And that's actually one of the outcomes, or one of the anticipated things from the Mega Movie project, to see if the light from that star, given the potentially millions of observations, is indeed bent by the amount that is expected. So we can go back in time to our 1919 time capsule and actually verify that Eddington verified that general relativity actually was correct. Of course, now we have beautiful gravitational wave detection, so maybe general relativity is in a lot less doubt than it was in 1919, but I think that's one of the potentially exciting experiments, spin-off experiments that we're going to have.
Wait, the original question was past advances, right?
Right.
Okay. The perfect person to talk to about that is Jay Pasikoff at Williams College.
Jay, you want to say something?
Hello, thank you. And I can also say that I'm very pleased that my group has had for the last couple of years a big grant from Carey's Atmospheric and Geospace Science Division of NSF. So we'll be in Salem, Oregon with a lot of experiments. I also have a new article in Scientific American that just came out answering some of these questions that you can look at, the August issue, and something coming out in a week or so in Nature Astronomy for the last 10 years of advances in solar research. But just to pick a couple of examples, at the eclipse in 1868, helium was discovered. So that's not bad, element number 2. It took the chemists over a couple of decades before they caught up with this. Then the next year, there was another spectral line seen, and you'll see this on my slide and the poster outside. There was a green line found, so they said coronium, after all, parallel to helium. And then that took 70 years or so before it was figured out and turned out not to be an element, but rather to be million-degree gas in the corona. And one of the things we'll be studying with my NSF support is the ratio of the green line and the red line in the corona, which shows how the temperature of the sun, of the solar corona, varies over the sunspot cycle. And I make the point that the sun is just a laboratory that's conveniently only 8 light minutes or 93 million miles away. And there are millions and billions and trillions of other stars that have these parts of the atmosphere, million-degree coronas, for example, that we study best in the sun and then extrapolate. So we're basically finding out how the sun shines and how the stars shine.
Thanks, Jay.
Thank you, Jay. Other questions? Go ahead, Nicholas.
Great, thank you guys. So just to follow up on something you were saying earlier about photos on social media, Facebook and such, and how those can contribute to the science we're learning during this eclipse. 2 questions. Has anyone contacted these big social media giants, whether it be Twitter or Instagram or Facebook, to, I don't know, get the message out that users' photographs can be useful for science? And I know you've made a partnership with Google, but there are other ones out there where there are a lot of photos as well. And then the next one, to that single person who's taking a photo, an Instagram photo or something during an eclipse, what do you say to them to kind of convince them that that one photo, in addition to getting many likes on their social media, can contribute to science? How do you get those people to upload their photos?
Well, I want to start with your last question, because everybody has a unique perspective. So wherever you are, however you're looking at it, we want to see that perspective. As for partnerships, I'm not sure. Has NASA done something?
Yes, and I'm a little bit far away right now from NASA headquarters. There is just every day new stuff is going on. And so I don't know the details. Of course, we have all the accounts, whether we have actually made contact with them, but this is an idea that I will check on. I do want to say one thing, and that is, I would like to say that please don't get carried away by taking your personal picture. Just observe what you have been presented with. The eclipse is very short. If you're lucky, you're going to see 2 minutes and some odd seconds. Please look at the corona. Maybe take one picture. Science, you can, other science, if you are with a team, you can do, but it takes away. If you're just a citizen and have not participated, please enjoy this cosmic show.
Yeah, because I would say that your eyes are the best way to see the colors and the vibrance and the change of the colors. But invariably, the handheld devices are autonomous. So you can hold it, and it goes. Then you look. But remember the glasses thing, right? Really, really important. But, we hope to be able to harvest all the images. We have ways of trawling. And so the idea is to then communicate after the fact, probably, and start to pull more in. So,
I kind of want to, add to what Carrie said. I mean, that's also kind of very important. That's why we have actually amateur astronomers really taking observations from many different vantage points. One of the things that probably we will do is, we can't say this yet depending on the quality of the data, is really apply machine learning, deep learning, AI, to see if we can pull out details that are not ordinarily available to us. We are already doing that with our big data because, as human beings, we can only crunch so much. And it's kind of a fascinating area we are embarking upon.
Well, if you think about it, potentially billions of images. Sampling an event that's only 91 minutes in duration from coast to coast means that you have super duper high cadence, right? So you're super slow-mo corona. So the ability to study waves in the corona, to study small eruptions in the corona will be visible in those super slow-mo movies that we've never ever had before, and we even can't get from space. Even in space, our image sequences are limited to a few second exposures. So if you're talking about nanosecond exposures, that'd be pretty freaking cool.
Thank you. I think we've got a question from online.
We have a question from Rachel Lalensack at Nature. Rachel, I'm about to unmute you.
Hi, can you hear me?
Yes, we can hear you.
All right, great. Yeah, so my question here, and kind of going off what Nick was asking earlier regarding citizen science, I kind of want to just really clarify the scale of this event as a one-off in terms of one-off citizen science projects. I mean, you just mentioned, this is very short for one. It's one day only, once in a lifetime, 91 minutes from coast to coast. Any given individual has a matter of seconds, minutes to observe this. So, in that kind of reference, what is the scale here in comparison to other one-time events of citizen science participation?
I'm not sure we know yet.
Well, and it's really not just once in a lifetime, because in 2024, you could even see this is a dry run for 2024, if you want to go that far. But I think, in terms of scope, I think for me, it's the ability to engage the citizenry of the US and those from around the world that are coming here to see the eclipse about the Sun-Earth connection. So I think it would hopefully kickstart a lifelong love of the sun and the earth and how they relate. But once you see that eclipse, it's kind of like a drug. Maybe Jay would agree with me that you want to see another one. And then you want to see another one. And so I think that this guy coming up is a Kickstarter for us, and to be more adventurous. Even though some of the citizen science experiments that we're going to feature today are really adventurous and really innovative, who knows what comes up for the next one based on what we learn from this one. So I think it's just a start.
So, would you say, sorry, go on, finish your question. I want to add a few more sentences to that, but finish your question.
Yeah, so I mean, would you say it's the biggest this far compared to, I mean, NASA has like Globe Observer app, but that's ongoing. It, you can always submit to it and things like these. So there's other citizen projects that are not really like one-off on this kind of shorter time scale event. There's the Christmas bird count, things like that happen once a year. So in that scale, how does the scale compare to other citizen science projects?
It is one-off in every single way. You do not have an opportunity to engage every individual in a continent in an event that actually teaches you about physics. A lot of people still don't believe, right, that the moon goes around the earth goes around the sun. Here we are predicting this eclipse with utmost precision. We are actually teaching physics. We are bringing that knowledge to everyone who is participating in this. So I think that is the most unique aspect of this eclipse. It's not only a transformative cosmic event, but it is actually teaching you about our universe in such a deep way. It's not just solar physics, right? Eclipse is the technique by which we learned exoplanets. Eclipse measurement of animals in a zoo would be just fascinating if you can imagine. I know at least one group in Columbia, Missouri is going to do this. If you guys write about it, maybe many more will. Capturing animal behavior. What we have data of are one-off from individual eclipses that happened in remote places. This is giving us the opportunity of the entire swath of 2,500 miles of totality, but entire continent. So I think there's nothing as unique as this. That's all I can say.
And if I can add one thing to what Lika said, in full agreement with Lika, take a kid to the eclipse. This can be absolutely inspirational. All 50 states have a partial eclipse, even Alaska and Hawaii. And every 3-year-old can be very struck by it. Every 9-year-old can learn that if he or she pays attention in school, takes some math, takes some science courses, that these people can also predict the universe to the precision that Lika just mentioned. So this, without apps and without anything, just being outside looking up, supervising your young children to use of the filters properly, but to have the kids outside experience the sky going dark about them, the light colors changing, everything being eerie. You lose all that on TV, even on the NASA app. You have to be outside to experience it, but it can be inspirational to a new generation of students. And what scientific advances we'll get in 20 or 40 years from the 10-year-olds of a month from today, we'll have to wait to see.
It's a very good point.
Thank
and
you, Jay.
This kind of reminded me something I didn't get a chance to say. At least in my mind, I look at this eclipse as a generational eclipse in some ways. You know, we are all going to participate in this. And I think post this eclipse, perhaps 50 years, 100 years from now, when we talk about this eclipse, the reference would be there was a generation before this eclipse, and there's a generation after this eclipse. This eclipse has that power, and it can only happen if all of you engage in it and communicate this.
Thank you. Do we have more questions?
Somebody
Go
should
for
just
it.
hand him the microphone.
Go for it, Nicholas.
Just one more question. Of course,
If you could, I'm sorry, if you can go to the mic. We've got a number of people listening remotely. Thank you.
one more question to kind of follow up on everything that's been said, especially with what Jay has been said. Of course, there'll be millions of people in the line of totality, but how do you excite the rest of this country that won't be in the line of totality, that will only experience a partial eclipse? How do you excite them and make them realize that, yeah, this is still something exciting, something big for them? When I'm speaking to people, they'll always ask me, oh, so is it happening in New York? And I'll say, no, you have to be somewhere in the middle of the country. And then they kind of tune out. They don't realize that there are still aspects of the eclipse that impact them. So what is NASA doing, or how do you kind of excite the rest of the country that won't experience totality?
Well, I'm going to speak on behalf of NSF here. We could get to NASA in a moment. But when I talk to people about the eclipse, I tell them everybody can see it from wherever you are, you can see some part of it. And when I was in elementary school, there was a partial eclipse, and I was way up in Vermont. I don't know the path of it. But I remember we all went outside and we looked at it. It wasn't, you couldn't see totality, but it was exciting enough that they took us out of school so we could go take a look at it. So tell them, you can see it, you can see some part of it, and it's really, really cool.
I think most people haven't seen even a partial eclipse. Imagine seeing a crescent sun during midday in August. I mean, if that's not cool, I don't know what cool is.
Yeah.
That's how I feel. But the way you connect them is that you tell them that you're going to feel a difference in temperature. You can, wherever you are, I mean, if the eclipse is even 95%, where you are going to see a change in the ambient light. You are going to feel a temperature difference. You will feel darkness descend. You are going to see stars during the day. Tell them that. So have you ever seen a star during the day other than the sun? Yeah.
Something amusing, Scott.
Yeah.
Do we have other questions from reporters? Anybody online with a question? Anybody in the room? Any of the reporters in the room? Go ahead. Okay, we've got a question from a reporter in the room here.
Hey, it's Corey Reppenhagen from 9 News here in Denver. My question is about communications. So you briefly talked about the effect of space weather on communications. Can we blame bad cell days on space weather? And will August 21st perhaps be the greatest cell reception day ever?
It's the day the internet died. I don't know. I think one of the aspects that we've heard a little bit of from the Google people in particular is, will the internet stand up to the traffic on the 21st? They expect to see a large rolling bump in bandwidth going across the country. So there could be all kinds of unanticipated things. I wouldn't go so far to say that it'd be a bad cell day, but I think cell traffic could be pretty bad.
He was referring to, I think that it would be a good cell day because the visible disk of the sun is going to be covered. But what you have to remember is we are seeing the corona. We're seeing the corona in white light, but there is still a great percentage of XUV and extreme ultraviolet rays in that totality, and that will absolutely have impact on the ionosphere. So those rays travel at the speed of light, about 8 minutes, and depending on the conditions, that's how the ionosphere gets ionized. In terms of other disturbances that we are talking about, normally it takes several days, depending on the speed of a coronal mass ejection, to get to our planet, right? So if something was launched like a day ago or 2 days ago, depending on its speed, would still be arriving even when the sun is eclipsed. So I don't think we are predicting anything.
Yeah, that's a good point.
That's a very good point.
Okay, Charlie?
To go totally provincial, maybe this would be for Scott, or my question would be, what % of totality will we have right here in Boulder, Colorado? And somebody had mentioned to me some time back that the difference between 90 or 95 to 100% totality is very dramatic, and that if you have the opportunity to be in the 100% totality zone, that's where you want to be. What will people see? What degree of totality will they experience right here?
Good question, Charlie. Point.
It's there's interactive map at NASA that you can pull. You can just put your city name, latitude, long. It will give you all the information of the order of, I think, 93 to 95% is what I am remembering. And this is really not, even at 99%, of course, you don't see the corona, right? At 95%, you begin to sense the change in ambient light. But you're absolutely right. And I would say not just 95%, even 99.9%. Seeing 99.9% versus the totality is like the difference in night and day.
Literally.
Literally and figuratively.
Yeah. Okay, I think we're at the end of our press conference then. I want to thank all of you for attending. For the reporters in the room, we have, in addition to the panelists, we have scientists from across the country who are available. For those who have been following online, we'll have talks later in the day that you could follow online, and if you have questions about that, please send me an email and I can send you the link. My email address is my last name, Hosansky, Hosansky, @ucar.edu. Thank you, everybody.